Myself Anju, PGT Chemistry from Government Senior Secondary School Badwasni, Sonipat. My mentor name is Ma'am Anju Singla. Students, today I am here to discuss with you the second part of the topic haloalkanes and haloarenes, which is considered in class 12th Organic Chemistry. In previous session, we already discussed about the general introduction of haloalkanes and haloarenes, their properties, their daily use in life, their reactions, and how we prepare haloalkanes and haloarenes. All procedures are discussed in part 1. So today we continued with the reactions of haloalkanes and haloarenes. Students, let's recapitulate some things. Firstly, what are haloalkanes and what are haloarenes? Haloalkanes are the alkanes containing halogens, and haloarenes are the arenes containing halogen. So, we continued with the reactions of haloalkanes and haloarenes, and these are nucleophilic substitution, elimination reactions, and reactions with metals. So, about the nucleophilic substitution reactions. In nucleophilic substitution reactions, as you see in the slide, in this type of reactions, a nucleophile react with a haloalkanes, which described as a substrate, having a partial positive charge on the carbon atom bonded to a halogen. As you see here is a nucleophile react with a haloalkanes, halogen containing alkane, in which alkane have partial positive and halogen having negative charge is bonded on the carbon atom to a halogen. A substitution reaction takes place and halogen is called the leaving group, departs as a halide ion. Since the substitution reaction is initiated by a nucleophile, so it is called a nucleophilic substitution reaction. It is one of the most useful class of organic reactions in halides, in which a halogen product is formed by the reaction of haloalkane with some nucleophile, as you shown in slide. Here the things we required or we get is a nucleophile, a substrate, and a leaving group, which is a halogen. Types of nucleophilic substitution. Further, nucleophilic substitution reactions are also divided into two types. First is substitution nucleophilic bimolecular, called as SN2 reactions, described as SN2 reactions. Second is substitution nucleophilic unimolecular, described as SN1 reactions. Before understanding the types of nucleophilic substitution reactions, let's recall about nucleophile. The first question arises in your mind is, what is a nucleophile? A nucleophile is a nucleus-loving species. The species which liking positive charge. Greater the electron negativity of halogen attract the share pair of electron, so it becomes slightly negative. The bond is non-polar. They are electron pair donors, possess at least one lone pair of electron, are attracted to the slightly positive electron deficient species, slightly positive carbon, and the example is water is a poor nucleophile. Water is the example of a poor nucleophile here. So now about the nucleophile, we continued with the substitution nucleophilic bimolecular reactions. SN2 substitution nucleophilic bimolecular reactions. These are known as second order kinetics followers. This type of reactions occur in one step through the formation of a transition state, as you shown in the picture. Here we see that this is known as bimolecular reactions. It is depicted as a bimolecular nucleophilic displacement reaction. In these reactions, the incoming nucleophile interact with alkyl halide, causing the carbon halide bond to break, while the formation of a new carbon or nucleophile bond is there. These two processes take place simultaneously, as you see in the transition state. The process of formation of bond and breakage of bond take place simultaneously in this transition state. This is known as two-step process take place simultaneously in a single step, and no intermediate is formed here. As the reaction progresses and the bond between the nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. As this happens, the configuration of carbon atom under attack invert in much the same way. As you see, umbrella is turned inside out. This process is known as inversion of configuration, and the process is known as Walden inversion. SN2 nucleophilic substitution is a bimolecular reaction. Nucleophile combined with alkyl halide to form a pentacoordinate transition state, and the slowest step is the rate determining step. Here entitles two species, alkyl halide and nucleophile. So the rate of reaction is depend on both of the substrate. The alkyl halide and the nucleophile both are on both rate of reaction is depend. SN2 reactions basically follow a concerted mechanism. Now the question arises is, what is a concerted mechanism? Concerted mechanism is a mechanism which happens in just one step. One step process it is, so it is known as concerted mechanism. If it is a two-step process, then we never called it the concerted mechanism. Here a transition state is formed in which formation of one bond and broken of one bond takes place simultaneously. In SN2 substitution reactions, we use polar aprotic solvents, and the example of polar aprotic solvent is acetone. Why aprotic? Because I don't want liberation of hydrogen ions. It don't donate hydrogen ions. So alkyl halide react with a polar aprotic solvent. Nucleophile attack from back side, not come from front side, because in front side it will face so many repulsions from X electron negative atoms. And what is X here? X is a halide, ion here, halogen here. So nucleophilic attack from back side and form a transition state. We obtain a nucleophile with alkyl group as a product. We get an inverted product here. The inversion of configuration is known as Walden inversion, accompanied by inversion of configuration. Reactivity of alkyl halides in SN2 reactions. The reactivity depends upon steric hindrance, and the meaning of steric hindrance is bheed ho jana. The reactivity which is depend upon steric hindrance caused by the alkyl group attached to or near to the carbon atom to which halogen is attached. More the steric hindrance in alkyl halides, lesser will be the reactivity. You see here, I take here methyl, primary, secondary and tertiary groups. In tertiary group, there is 3 alkyl groups are attached. And the 3 alkyl groups here don't allow any nucleophile to react on them or attack on them or attack on that carbon atom because of the steric hindrance created by these alkyl groups, these larger bulkier groups. So the reactivity depends upon steric hindrance, shows that on tertiary halogens this is impossible, this is very tough of a nucleophile to attack on that carbon containing tertiary groups. In secondary halogens, there is only 2 alkyl groups are there. So this is less steric hindrance there experienced by a nucleophile as compared to tertiary. And in case of primary, this is very low. And in case of methyl, there is no steric hindrance. So the reactivity is, methyl is more reactive, fastly reactive than primary, then secondary and then tertiary. So the reactivity depends upon steric hindrance. Steric hindrance hindered the attack of nucleophile on the carbon atom. Now, I think SN2 bimolecular reactions are clear to you. Let's continue with SN1 reactions. SN1 reactions are substitution nucleophilic unimolecular reactions. As the name indicates, SN1, here the rate of reaction depend only on the alkyl halide, not on the nucleophile. So the rate of reaction is depend only on one species. So it is called the first order. They follow the first order kinetics. Here in the picture you see that this is a two-step mechanism. In first step, nucleophile detach itself from the substrate and give us a stable carbocation. And in second step, then the carbocation is attacked by a nucleophile, and this is step 2 and we get our product. This is a two-step process. One step is slow step and second step is fast step. As all of you know that the slow step is always rate determining. And here the positive point is that we form a carbocation here, which is very stability. Now, substitution nucleophilic unimolecular reactions. Firstly, the rate depend upon concentration of only alkyl halide, not on the nucleophile. Only one species, this is alkyl halide. Rate, alkyl halide, rate of reaction is 1. So, they follow first order kinetics because the order here is only 1. So, it is known as unimolecular. They carried out in polar protic solvents, and the polar protic solvents are water, alcohol and acetic acids. First order kinetics they follow, we already discussed. They occur in two steps. In first step, carbocation is formed, and in second step, carbocation is attacked by a nucleophile to complete the substitution. Reactivity in SN1 reactions. Greater the stability of carbocation, greater will be its ease of formation from alkyl halides, and faster will be the rate of reaction. In case of alkyl halides, tertiary alkyl halides undergo SN1 reaction very fast because of the high stability of tertiary carbocation. So the order of reactivity is tertiary halides are more reactive than secondary halides and the primary halides. So you notice here the reactivity in case of SN2 and in case of SN1. These are opposite. In SN2 the reactivity of primary halide is more, and in SN1 the reactivity of tertiary halide is more. The factors affecting SN1 reactions. The first factor is the type of carbocation. Stable the carbocation formed, faster is the SN1 reactions. The stability order is tertiary, secondary, primary and methyl group. Alkyl groups are electron donating, so tertiary carbocation is most reactive to SN1 reactions. Second is type of nucleophile. Rate by which the reaction is happening. The speed of reaction. Rate does not depend upon nucleophilic concentration as shown in rate reaction. So I can take a poor or strong nucleophile. But in case of SN1, we take here a poor nucleophile. If I take a strong nucleophile, it will try to interact with alkyl halide in a very fast manner. That is, it doesn't give time to the formation of carbocation. Here you see in the picture in the reaction, the formation of carbocation in first step, in slowest step. So if we take a strong nucleophile, it will interact very fast to alkyl halide. Or in this fast process, it does not give time to the formation of carbocation. So strong nucleophile may lead to only a one-step process. But in SN1 reactions, there is a two-step process. So here we use a poor nucleophile. Leaving group, which leaves the substrate. Two types of leaving group are there, good and bad. Good leaving group is having enough space within it, enough capability to hold or disperse the negative charge inside it. And the example of this is best leaving group is iodine, then bromine, then chlorine, and then fluorine in case of halogens. The reason is iodine has biggest size, so enough space for holding electrons. Good leaving group will leave the substrate quickly. Now, polar protic solvent. The fourth point is polar protic solvents. It must have the polarity. Polarity means positive and negative, both charge are there. It must have proton donating capability, so they ready to give H positive ions, hydronium ions. For example, water and acetic acid. So we use polar protic solvents because it helps in cleavage of alkyl halide bond. Because since it is polar, it will be having positive and negative poles, which will try to attract alkyl halide bond. This is also having poles in it. Due to such polar interactions, this bond, alkyl halide bond, more likely to cleave. So we use polar protic solvents. Rate of reactions depend upon slow step. The question arises in your mind is that why always rate of reaction depend on slowest step? Why slow step is rate determining? So the answer is there, the answer of your query is there, because fast step is so much fast. We can't find out the concentration of all species involved in reaction. It is very difficult to observe such a fast step as compared to slow step. In slow step, I can very well find out the amount of each and every species involved in reaction, and that is how we defined a rate of this reaction. So every time slow step is rate determining. आप सब देखते हैं, अगर हम कोई काम बहुत फास्टली करते हैं तो हम उसके अंदर इन्वॉल्व होने वाले सभी स्पीसीज के बारे में, हमने उसके अंदर क्या क्या इन्वॉल्व किया है, क्या क्या यूज किया है, उसका हमें पता नहीं चलता है, हम उसे डिटरमाइन नहीं कर सकते हैं. बट अगर हम किसी काम को बहुत स्लोली करते हैं, स्टेप बाय स्टेप करते हैं, तो हमें एग्जैक्टली पता होता है किस चीज की हमने, किस स्पीसीज की कितनी अमाउंट को इसके अंदर हमने इन्वॉल्व किया है, हमने कैरी किया है, और हम उससे उसका रेट एग्जैक्ट, उसकी क्वांटिटी हम पता लगा सकते हैं. इसलिए स्लो स्टेप आपका हमेशा रेट डिटरमिनिंग होता है. नाउ द स्टीरियोकेमिकल एस्पेक्ट्स ऑफ SN1 and SN2 reactions. In SN1 reaction proceed with a complete stereochemical inversion. I give you the example of inverted umbrella here. While a SN2 reaction proceed with the racemization. So firstly discuss about SN1 or SN2 reactions. Firstly we know about the stereochemistry. What is stereochemistry? Stereochemistry is a branch of chemistry which involves the study of relative spatial arrangements of atoms that form the structure of molecules and their manipulations. Plane polarized light. You see in this picture, the plane polarized light consists of waves. in which the direction of vibration is the same for all waves. Light may be polarized by reflection or by passing it through filters, such as certain crystals like this nickel prism that transmit vibration in one plane, not in other planes. This is known as plane polarized light. Certain compounds rotate the plane polarized light which is passed through a nickel prism, or ordinary nickel prism. When it is passed through their solution, such compounds are called optically active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. If the compound rotates the plane polarized light to right direction in clockwise direction, it is called as dextrorotatory, and we define it as D form. It is indicating by places positive sign before the degree of rotation. And if the light rotates towards anti-clockwise in left direction, it is known as levorotatory, and we define it as L, and which sign is possessed is negative sign. Now, optical activity. The substance which can rotate the plane polarized light is called optically active substance, and the property of the substance to rotate the plane polarized light is called optical activity, and the phenomenon is called optical isomerism. Two types of optical activities are there. First is levorotatory, second is dextrorotatory, as I discussed before. A substance which rotates the plane polarized light towards the left side is known as, in anti-clockwise direction, is known as levorotatory, and we define it from negative sign. Dextrorotatory, a substance which rotates the plane polarized light towards right direction in clockwise direction, is known as dextrorotatory, and we assign it positive sign. Optical rotation and specific rotations. Firstly, the optical rotation is the angle through which plane polarization is rotated either towards left or towards right is called optical rotation, either in clockwise direction or in anti-clockwise direction. Next is specific rotation. It is defined as the number of degree of rotation observed when the concentration of optically active substance is 1 gram per centimeter cube and the length of polarimeter tube is 1 dm for sodium vapor lamp at 25 degrees centigrade. Next is our chiral carbons. A carbon which is attached to 4 different groups is called a chiral carbon or asymmetric carbon. Chiral objects which are non-superimposable on their mirror images are called chirals, and the property of non-superimposability is called chirality. Achiral objects which are superimposable on their mirror images are called achiral. Students, these are the small definitions which come in exam in 1 marks for board exams, and 2 or 3 marks also with differences are there. The differences between chiral and achiral. What are chiral carbons? What are achiral carbons? What is optical rotation and specific rotation? These are the small questions which are always present in the question paper of board 12th class. Next is our enantiomers and diastereomers. Enantiomers, the optical isomerism which are non-superimposable mirror images of each other, are called enantiomers, and the phenomenon is known as enantiomerism. These have identical physical and chemical properties but rotate the plane polarized light in opposite direction to equal extent. Diastereomers, the stereomers which are not mirror images of each other, are called diastereomers. So here the question arises, differentiate between enantiomers and diastereomers, and this is a 3 marks question, always arise in the 12th class board exam. Next is racemic mixture, retention, inversion and racemization. Firstly, the racemic mixture. An equimolar mixture of a pair of enantiomers is called racemic mixture or racemic modifications. A racemic mixture is optically inactive because a racemic mixture contains two enantiomers D and L, dextrorotatory and levorotatory in equal proportions, which have equal and opposite rotation and hence cancel the rotation of each other and become optically inactive. These are defined as racemic mixtures. Next is retention. Retention of configuration is the preservation of spatial arrangements of bonds at an asymmetric center during a chemical reaction. Inversion. Inversion of configuration is the inversion of spatial arrangement of bonds to an asymmetric center during a chemical reaction. Next is racemization. The process in which both retention and inversion of configuration take place simultaneously during the reaction is known as racemization. The product is optically inactive as one isomer will rotate plane polarized light in equal and opposite direction to the other isomer. Hence, the rotation of each other is there. Now, we continue with the second type of reactions. These are known as elimination reactions. Elimination reactions are the reaction where starting material loses the element of a small molecule such as hydrochloric acid or water or dichlorine during the course of reaction to form the product. Here we only discuss about the beta elimination. Beta elimination means the elimination here is we discussed on beta carbon atom, not on the alpha carbon atom. So the elimination reactions held on the beta carbon is known as beta elimination reaction. When a haloalkane with a beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is an elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. As a result, an alkene is formed. As you see here, an alkene is formed as a product. Since beta hydrogen atom is involved in elimination, it is called as beta elimination reaction. Here is the possibility of formation of more than one alkanes due to availability of more than one alpha hydrogen atom. Usually here the alkene formed is the major product. So these are known as the beta elimination reactions. Next is reactions with metal. Most organic chlorides, bromides and iodides react with certain metals to give compounds containing carbon metal bond. Such compounds are known as organometallic compounds. An important class of these organometallic compounds discovered by Victor Grignard. Victor Grignard, a scientist who discovered, we know about Grignard reagent. We discussed, we did reactions of Grignard reagent which are given by Victor Grignard. The reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether gives us Grignard reagent. In the Grignard reagent, the carbon-magnesium bond is covalent and highly polar with carbon pulling electrons from electropositive magnesium. The magnesium halogen bond is essentially ionic. Here in Grignard reagent, we defined it as RMgX. R is an alkyl or aryl group, Mg or X is a halogen. Grignard reagents are highly reactive and react with any source proton to give hydrocarbons. Even water, alcohol, amines are sufficient acidic to convert them to corresponding hydrocarbons. It is therefore necessary to avoid even a trace of moisture from Grignard reagent. On the other hand, this could be considered as the one of the most important method of converting halides to hydrocarbons. You see in the reaction. Next is our Woods reaction. This is a name reaction and this is also very important. Here, alkyl halides react with sodium in dry ether to give hydrocarbon containing double bond. Double the number of carbon atoms present in the halide. Here you see the alkyl groups are doubled in the product. In the presence of dry ether, this reaction is performed. This is known as Woods reaction. Next is Woods-Fittig reaction. A mixture of an alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether, and it is known as Woods-Fittig reaction. So the next reaction, I already discussed about Fittig reaction and Woods-Fittig reaction. Let's recall. Fittig reactions are the reaction in which aryl halide also give analogous compound when treated with the sodium in dry ether, and this is known as biphenyls. In Woods-Fittig reaction, a mixture of alkyl or aryl halide gives an alkyl arenes when they react with sodium in the presence of ether. And another named reaction is Ullmann reaction, in which a benzene iodide is heated with the presence of copper powder and give us biphenyl. These are the named reaction and these are very important for the purpose of exam. They come in the form of conversions. They come in the form of named reaction in 3 marks as well as in 5 marks questions. Is our electrophilic substitution reactions. Haloarenes undergoes the usual electrophilic reactions of benzene ring such as halogenation, nitration and sulfonation you see in the diagrams, and FRIEDAL reactions in which alkylation and acylation both are included. Halogen atoms, beside being slightly deactivated, is ortho-para directing. Ortho-para positions are substituted here. Therefore, further substitution occurs at ortho and para position, not on meta position. The ortho-para directing influence of halogen atom can be easily understood if we consider the resonating structure of halobenzenes. In their resonating structures, we see that the electron-rich positions are only ortho and para positions. In resonating structures, we see that. So, in electrophilic substitution, the substitution is take place on ortho and para position. First reaction is here halogenation, in which a chlorobenzene react with dichlorine in the presence of anhydrous aluminium trichloride and give us a product dichlorobenzene. So the product is minor and major. Minor product is ortho-directing and major product is para-directing. In the next step, nitration. Chlorobenzene react with HNO3 or H2SO4, sulfuric acid or nitric acid in concentrated form, and they give us the product chloronitrobenzene. And here is also two products. One is ortho-directing, second is para-directing, and para-directing is the major product. Next is sulfonation. Here the chlorobenzene react with sulfuric acid, concentrated sulfuric acid, and heated. So two products are formed. One is ortho-directing, another is para-directing, and the major product is para-directing, which is chlorobenzene sulfonic acid. So these are the three reactions: halogenation, nitration and sulfonation. Now we continue with the Today we discussed about the reaction of haloalkanes and haloarenes. First is nucleophilic substitution reaction, in which we discuss about SN1 and SN2 reactions. And the question arises here is, write the difference between SN1 and SN2 reaction. Second, why slow step is rate determining. And the third question is, where is inversion and where is retention of configuration is there. These questions arise in the board exam in 5 marks. Every year we see this question, and this is very important topic of this chapter, SN1 and SN2 reactions. Second is elimination reactions we discussed here. We discussed beta elimination reactions, halogenations, nitration, sulfonation. In electrophilic substitution we discuss. And in reaction with metals, we discuss about Grignard reagent and who give Grignard reagent and reaction of different metals here. And we discuss stereochemistry of reactions also. होप सो आप सबको समझ में आया होगा. आप सभी पूरे चैप्टर को दोबारा से रीड करेंगे और इससे रिलेटेड क्वेश्चंस को नेक्स्ट सेशन में हम डिस्कस करेंगे इफ एनी क्वेश्चंस आर अराइजेस देयर. सो फॉर नाउ द क्लास इज ओवर. थैंक यू.